Hello everyone and welcome back to another tutorial. Today I would like to show you how I created this gravel animation in Bifrost. And throughout this tutorial I'm going to make use of lots of high-level components. Most of them were provided by the community. So I encourage you to have a look at the Discord server, and I'm going to provide some links so you can get all the high-level notes from other creators, install them and follow this tutorial. So let's have a look at the graph. I'll give you an overview of all the different components that go into this, and then we can break it down and do one by one. So I started this by creating a rock generator to get some different gravels and little stones going on. And I set the collision shapes for a bullet straight onto my geometry. And here's a section where I created a grid and randomized the scale and rotation and the ID to feed everything into the instancer node. And then this is the bullet graph. Started off without the fields. So it's just the source node that is going to extract the collision shapes that I created on the geometry earlier, and set some parameters for bullet to be able to simulate everything. And I have my grid falling down into the ground plane, had it settle for, I don't know, maybe 50, 60 frames. Took one of these frames that I cached out here with this node and loaded this cache file right here, and then fed that back into the instancer node so we can have an initial state, and connected my fields. So this is a field section, and this goes with it. That's a Maya curve that I animated using Maxime's node to resize the strands. And I created a curve field with this, and outside of the curve field that is pushing the black gravels through the others, I wanted to see some movement, so I created a turbulence field, and all the other nodes that you're seeing here are just to drive the magnitude in the specific areas. So once everything is simulated and cached out, I have another section for everyone who's not rendering with Arnold. So if you do render with Arnold, you're good to go. At this point, you can start rendering your instances. But if you're rendering with Redshift, for instance, you'll have to jump through some hoops to get everything going with the Maya instancer. So there's another node provided by the community, which is a Python node that you can load into Maya as a plugin. And this will actually convert the arrays that we can put out, like point position, point scale, point rotation, and colors and everything, and feed this information into a point geometry that the Maya instancer can understand. So yeah, that's everything for the overview. We can start off with the rock generator then. Okay, so for the rocks, we're going to create a new compound, call this rockgen, hop inside, create a for each node, where the max iterations will determine how many rocks we're going to create. So we can expose it to our main level, or rename it to none or something. Hop inside, create a queue, and create a subdivision mesh loopable node. There are two versions of it. This is from a pack from HeydoubleU, and within a for each loop we need to use this one. Hook this up. There we go. And then we can already make a group, call this base, and organize ourselves. So the first thing we want to to do is vary the size. So I'll get a random value node, connect the current index, and the seed can be exposed. And then we'll hook this up to length, width, and height. Forgot to pipe up the min and max. Like this, put them into the group. And then we can maybe start with a minimum of 0.5 to a maximum of 1. There they are. And to display them a little bit more, we can spread them apart. So, for each loop, we'll go to the side. I'll need some space later on, so transform points, hook this up. Then we need a matrix, so we'll get the SRT for matrix node, hook up the transform, and the translation can be the parameter that we want to change. So we expose it, and we'll make this a flow 3. And then we multiply this with the current index. Since this is a long value, we need to convert it to float. Multiply, hook it up, and then add this to a new group. Agnostic, maybe rename it to offset, and then we can spread these apart just for display purposes. And we can make this a switch with an if node. So if it's switched on, we expose the transform points, and otherwise just get the pass node in between. It's more neat. Otherwise we'll just take the points at the origin, expose the condition, call this separate, hook this up and put it in a group. And now we can just toggle it. Alright, cool. So let's get back to only one copy. Get this out of the way. And now we can start to displace our points. The first displacement node is going to be displaced by a fractal turbulence fields. It's a bit much, but yeah, something like that. And we'll create another input node and expose all the parameters that we want to change. The seed needs to be randomized again, so I just copy the random value node from here, hook up the seed, kill the min and max connections, and make it go from 0 to, I don't know, some high number, and then convert this to a long, put this in between, and now if we create more of them, each and every one will have a different displacement. Cool. So back to only one copy. Maybe we can expose the number of subdivisions as well. And make a new input node. Expose everything to the top level and get organized. Make a new group, call it rough displacement. So that will be our divisions, the magnitude, frequency, number of frequencies in the seed. And then maybe we can up the resolution and continue on. What I want to do now is get some flat areas onto our rock, so it looks a little bit more like it's chipped off or something. And we can do this with a Voronoi pattern. So we're going to scatter points. Let's get a scope, point scope in a terminal to display the points. Too many. Let's start off with 10, right? And then we want to calculate the distance between each point on our geometry to the closest point on our scatter points. So we get the point positions from our sphere, our rock, and get the closest point node, and we'll find the closest points on our scatter, and then we'll compare these two positions. In order to do this, we'll take the get from array node, hook up the positions of our scatter, and get these indices. Then we can subtract the original position from the newly found closest points and calculate the length. And to make this visible, we can set the geoproperty color of type float. Since this is a float 3, this is a single float, so scale on to vector 3. Well, this is not necessary, it's just for display purposes. You can see that we have gradient now, which starts at 0 at the locations of our points and then increases. And this mask we can use to drive another displacement node. So let's get rid of the color, we don't need it, and use a displace points node and hook up the length to the weight. And by default, the displacement will displace out from the normals of the object. And since we do have normals on it, this will work. And as you can see, we're getting some dimples. And to mitigate this, we can use an F-curve node, put this in between, and flatten the curve like this. Cool. So now we can get rid of the scope, play around with the values. So we could, for instance, scatter mode, put this to blue noise, which will be a little bit more regular and create some more points. And this will look like a chipped off, happy little rock. So let's expose some of the parameters. The scatter mode, mount, randomize the seed. So getting these two nodes, follow the recipe, connect the seed, and maybe change the number. And then we might want to expose the F-curve. And we might want to expose the scale of the displacement. One level higher, another input node. Let's stop the graph. And get organized. So I create a new Voronoi group and add everything to it. And then we can continue on. Maybe get another subdivision node going. take the loopable. Maybe don't go too crazy. That's a bit much, maybe. Get 2 divisions going. And displace points node. And this does nothing because we just lost our point normal information. After the subdivision, there's no point normal, so we just need to update it. Update mesh normals. And then this will work again. There it is. So let's displace just a tiny bit and get a fractal noise field, which is just a scalar field, because I don't want to map the displacement vector. This should be displacing upwards from the normal. I just want to map the weight. That's still quite a lot of displacement. Maybe half of it. And then we can make an F-curve field to introduce some interesting shapes, like terraces. Maybe something like that. And if we up the frequency, number of frequency, and the frequency, we'll get something like this. And then we can make this even smaller and negate it, so it's eating into our geometry. And all the flat areas are pretty boring, and also the terraces don't look all too fancy. So we can add the noise that we were creating here onto our terraces that go out here. So just take an add node and add this together. Yeah, that looks better. So let's take an input node, expose some parameters, stop the graph, it's too slow. The seed will need to be randomized. And we might want to expose the F-curve too. And then up one level, input node, hook it up. Top level, organize. Make this maybe road group and add everything. There we are. Cool. So if you want, we could go ahead and make another displacement, even finer than the previous one, and expose this too for a high level frequency displacement. But I'm pretty happy with what we have. Let's create 10 different rocks. Change the seed if you don't like it. Change the size, or maybe just push them out a little bit more. That's fine. Happy little rocks. Yeah, let's continue on with creating our instances and then simulating bullet. So once you're happy with your rocks, you can cache them out or use a compute on frame node to write them into memory. And I'll do this at frame 0. So I'll have to jump onto frame 0 really quickly to get these cached. And then I go back to frame 1 and don't have to recalculate them. Oh, by the way, we'll have to redo it and turn off the separation so they'll all be at the origin. Right. So now let's create a point grid. This is one of Maxime's nodes. Have a look at the points and give them some more space and divisions. Maybe like this. Yeah, be more. And translate them up, because you want them to fall down onto a ground plane eventually. So now we can set instance geometry on our points, hook up our rocks. And this is what we'll get. And now we have to randomize them again by specifying the point instance ID. And make a new compound. Set instance ID. Hook up the points and get the point count. Make a random value array node. And this will give us values from 0 to 1 for each point. So we'll have to put them into the right range. Change range from 0 to 1. Put this into the range of 0 to whatever we like to specify. We want this to be an integer, so I'll make it to float. Connect this up to the end, floor. And convert back to long. Set geo property, point instance ID. Make this long value. Get the points connected. And rename this to max instances. Put in 10, since we created 10 rocks. Connected, and we'll get different rocks. Great, so now we can randomize the point scale from 0.5 to 1 and randomize the rotation. Which is specified in radians. I'll just crank this up. Great. So now we can have a look at the bullet nodes. All right. So we'll need to get the simulate bullet node and the settings, and we need from the rigid body menu source rigid body instances. The settings are easy. Start at frame 1, maybe decrease the substeps if we don't need it, and enable the ground plane. Hook this up to the simulator. The instances go into the source rigid body instances, which will just set a couple of informations for the solver to work with, like the physical properties, which are also mappable, by the way. We can check use point scale, and since we didn't specify any collision shape, this will just default back to whatever setting we're setting in here. Convex point count should be fine. Hook this up, export, And then we can start our simulation. Well, we might want to increase the friction on the ground plane. 2 or 3, I don't know. And then we can create a cache node. Make a file cache. And I'll give it a name. Here. Put this into write mode, and since we're copying our rocks onto our points as an instance shape, this will also be included in our cache file. But it makes it unnecessarily big, so we can just take all the parameters except for instance shape. And when everything is hooked up, hit play and simulate. Don't forget to put your timeline into play every frame mode. And just wait until everything settles, and then we can take this cache file, or one of the cache files, and use it as an initial state. Looks good enough. We'll just stop it right here. We can put this into pass-through mode, copy the node, paste it in here, specify a frame that we want to use. I'll take frame 50, read it, and replace our grid with our cache. Now we have an initial state. Now comes the interesting part where we do some animation with our bullet simulator. We could, for instance, inject velocities as fields. So we'll get the bullet fields node and a simple turbulence field. Let's make a vector field scope. Not too many divisions. Get a terminal and display it. And at this point, if the graph is getting slow, you want to view something, you can just disconnect the scatter. Since we just want to check our turbulence field, let's go to the vector scope and enable flow lines, make them longer. You can see it's pushing around in all axes, and I actually just want the points or stones to be stirred around at the ground level and only in X and Z, and just ignore the Y component. So I'll just get a multiply node. And a vector field. And then I'll specify X and Z to be 1 and Y to be 0. Multiply this, have a look. This will only push them around on a plane. And I also want to have a small fall off. So only the points that are on the ground level are being pushed, and the ones that are stacking on top should be unaffected, or nearly unaffected. They can freely roll around. And this means we'll have to get some kind of fall off going. We'll take a plane field, which will create a plane that we specify in here at the origin, pointing up. And this will be a scalar field, so we'll have to make a scalar field scope. So it's 0 at the origin, and then just increasing the value infinitely. So if we want to keep this in check, we can use change range node, or we can use a nav curve field. Oh, sorry. Right there. And then maybe go to position 3 and make this 0. And at position 0, I want the value to be 1. And then this will be 1 at the ground level and just decrease in magnitude. So put this in here to multiply it. And then we can see that the vectors are getting smaller right there. And this should be enough to steer our points around. Let's try. So we'll hook up the combined magnitude, the vectors into the acceleration of the bullet fields, and increase it to 50, or maybe 100, I don't know. Also maybe add some drag and see what it does. I'll just make a playblast, and then we can have a look at it. Okay, so after a couple of tries, I came up with some cool settings. I decreased the magnitude on the turbulence field to 20 and decreased the frequency to 0.3. Let's see what else. I set the drag to 1 on the bullet fields node, and I also decreased the friction, I think. Yeah, decreased the friction in the simulation settings node, so the ground isn't as sticky. It's just back to 1. And I cached it out. Remember, we killed the instance shape on the cache. So if you're just viewing the cache, you will only see the points. And if you want to see your geometry again, I'll just have to copy the set instance geometry node, put this over here, and set instance geometry again. And this is how it looks like. So particles are being stirred around by our field and happily colliding. Right now the turbulence field is pretty static, so we could change the phase by getting a time node and take the seconds, put this through a scale field and connect this to the time. And now this will change over time. And maybe we can decrease the magnitude later on, since this is not the main focus of our effect. We want to stir a couple of these particles with a curve field and push the others away with it. So this looks interesting. It might be just a little bit too much of movement, but generally this is how I started, and you can tweak the values later on. Okay, cool. So let's go ahead and make ourselves a curve field. Okay, let's start with disconnecting our graph, and let's make a node curve. Let's have going through our particles. Yeah, maybe something like that. Put this into our graph. And then we can hide it and output it in here. There it is. Need some more seconds. And then we can use the resize strands from Maxime to cut the strand. But this compound needs the ratio of the strand. So it should be 0 here and then increase towards 1 at the end. And the compound we need is update strand ratio. And this is a internal compound that is not exposed by default. You'd have to set an environment variable so you can see all the internal nodes. I'll post it in the description. And once we have the ratio, we can actually offset the strand like that. And maybe we'll start here, so -40. Expose the length into Maya. Here it is, -40. Let's set a keyframe, frame 1, and animate it all the way up. Make this linear. There we go. That's our animation. And what we also might want to do is update strand orientation. That's also from Maxime. And this will give us proper orientations on our spline. So we can build ourselves a curve field. Right, so with this curve, let's make a curve field. Make a new compound. And there's the strand, and then we're going to convert the strand to volume. We'll take the point to volume node and make that level set. And then extract a voxel field from this volume. We're going to need the voxel sign distance, which is a scalar field. And that is 0 at the points of our strand. And it's going to increase in all directions. We can make a scalar field scope to have a look at this. Make a terminal. And you'll see that right here, the values are small and they're getting bigger and bigger infinitely. So to better view this, we should make ourselves a probe geometry. Since we already have a strand, we can make a strand around strands from the Rebel pack. And use this as a probe geometry, for instance. Just have to increase the default value to 1 and the parent radius scale. Now, we don't want any twist on this. Just want to make more plies, maybe. And have that extend out a couple of times and make this also dependent on the radius that we want to set on our compound. So we make another compound out of this. Construct pro. And here we make a for each loop. And paste this, create strands around strands in here. And then we're going to merge geometries. Let's make 3 for now. And call this samples. Oops. And in here, we want to map the parent radius scale. Call this radius. And we're going to divide the radius by the max iterations, convert them to float, and multiply them with the current index. This will also have to be converted to float. Hook this up. And now we can expose the radius as well. So we make a bigger radius and more samples. And this will actually give us a really nice probe for our curve fields. Okay, so if we want to keep this in check, we'll have to change the range. Fields. So the minimum, maximum will be 1 and 0, and the old will be connected to our radius as well. So let's make this the radius. Hook this up on this side as well. We can expose the samples. And then set the radius to 3 maybe, like this. And then we'll see that our side distance field will decrease in value going outwards to the maximum of our set radius. And this will be able, let us control the magnitude with our curve field. Okay, so what else do we need? We might want to control the magnitude along the spline as well. So we calculated the ratio over here, which will be propagated by our points to volume into a volume component. So we can take the voxel ratio and have a look at this one. So here you can see that at one point the values are 1, and on the other end the values are 0. And it depends on how we created the spline. And if we reverse it, then it will be 1 here and 0 over there. So that's fine. And for both of them, we can introduce a F-curve. This F-curve will be the fall off. And this F-curve will be the ratio. Okay. Now this is our two magnitude multipliers. And now we have to worry about the directions. So make a vector field scope. And then we'll take a voxel fields node and change its type to vector, because we need directions now. And we're getting the tangent. Hook up the probe. And this will be the direction along our strand. Now, since we already have a scalar field with values that are increasing, going outwards, which is the side distance, we can just take the gradient of it. The gradient field of the scalar field will be a vector, and this will be pointing outwards. And since we have the vector pointing along and the pointing away from it orthogonally, we can just make the cross, and the cross product will give us the third axis, which will be around our spline. So these are our three directions, and we simply have to multiply them with magnitudes. So we will multiply the gradient fields, make another scalar field and multiply it. Call this waveform axis. The tangent fields we will call a long axis. And the last one is a round axis. Now these three can just be added up. And can be multiplied by the two fall-off scalar fields that we have. One is the ratio, one is the fall-off. And then we have our final vectors. So let's see if all of this works. For the ratio, we'll just keep everything at 1. Make this linear. Make the value 1. The fall-off is fine, and then we want to point along the axis. Cool. And you can clearly see that the vectors have a higher magnitude in the inner core where this line is at, and it's diminishing towards the end of our radius. And then there is away from axis and around axis. And you can combine all of them somehow. And let's activate the flow lines. And then we see that we have a properly working curve field. Great, so let's just output the final result and call this curve field. Okay, so now that we have our curve field in place and our strand is animated, we can go ahead and add this to our velocities. Let's just get the turbulence out of the way and create an add node. Get the turbulence, get the curve fields, and add them together. Have a look at the vectors. This is what it looks like. Our curve field is cutting through the turbulence. Well, I think, well, maybe, yeah, we could separate both fields a little bit more by multiplying them with a magnitude. And let's get a scalar field scope and create a mask for our curve field. We have a vector here, so we can take the length of it and then create a mask field. And the mask field will be one wherever we have vectors present, and it will be 0 where there is no vectors at all. So if we have a look at this scalar field, and this is what it does, right? We have a mask wherever we have magnitude or velocities on our curve fields. And we can simply invert it by making a scalar field with a value of 1, and then subtract the mask. And now to view this properly, we'd have to change the scalar field scope. You can see the hole, but it's not as clear, so I'll just trim this. So yeah, this is what it does. If it's inverted, it's kind of cutting through. And wherever we have red points, this is where our turbulence should be. So we can take the result and add this to the multiply node that we created earlier for our turbulence field. Then this will be added. And if we have a look at the vectors now, they're much more clearly defined and not affected at all by the turbulence. Let's just disconnect it. You can see the difference here. So it's not always desirable, but for the fact I wanted to do, this tended to be the best way. Here's the add node. We'll just get rid of this. and add it to the fields. And then I'll make another cache. All right, so here's the result. We have a cache where we can see that our points are being pushed with our curve field. And if you have more points than this, they will stack up nicely, and the effect will be a little bit more interesting. But yeah, that's it. Let's get the colors going. So let's first create a random color, a randomized geo property, and we'll take the point cache and disconnect the set instance geometry node. We just don't need to see the stones anymore. We can simply have a look at the points and set point shape, make them disks, maybe a little bit smaller, and then we are going to randomize the geo property called color and set these values to be of float 3. Here they are, our random colors. And we might just keep the blue channel black, completely black. And then we're going to color in some of these points with a mask in a certain radius around our spline. So let's get the point positions of our strands. So get point position. And get points in radius. Get the positions from the strands and connect our point cache. And this will give us indices, but it's a nested array. So for each point on the curve, there will be multiple points in our point cloud that will be identified within the radius that we can specify here. So make that a radius of 3 units and flatten this array. And now we're going to split up these color values here. Vector 3 to scalar, so we can look at this individually. So XYZ stands for RGB. The blue channel is completely black, and this is where we want to inject a white color. So set an array at these indices, a value of 1. And then we can combine this back together. So scalar to vector 3, get the R, G, and B, set geo property color. It's a float 3 attribute. And now the blue channel has a black and white mask, basically. So if you just turn off the other channels, this is what the blue channel looks like. And right now, this is evaluating at each frame. So the colors are kind of moving through our point cloud. It's not desirable. So we just compute this on the first frame. On frame 1, I'll get the colors and setting them onto the geometry. All right, so let's get to the instancing part in Maya. First thing we should do is output all of our rocks into Maya. So I just output the values, and I'm using the Bifrost Editor Plus extension from HeydoubleU to output all my rocks into Maya. So here are the 10 geometries, and this will create the standard way of doing things at the moment, extracting the information from Bifrost, going into the Bifrost Geo to Maya node, and then connecting all of these meshes to an empty poly surface. And now we have to convert all the information that we have on our point geometry to make it compatible with the Maya instancer. And we are going to use a node provided by Rodolfo from the Bifrost Addicts Discord community, which is called Bifrost 2 Instancer. Now I changed this up a little bit. You can download his original version or take mine, and I'll leave this for you to download. I just extended it with a point color attribute, and I promoted the point size attribute from a single float to a vector. And we just need to output all of these information and hook this up. So let's go in here, get point position, and get point orientation, which is one of Maxime's node. Let's pass this through an empty node. Now this is a math float 4 because it's a quaternion. I just have to convert this into Euler space. So returning to Euler. XYZ rotation order is fine, and just convert the radians to degree. And this will be our out rotation. Then get point scale, also from Maxime. Get geo property color. It's the one we just made. And get geo property long. I'm sorry. Point instance ID. So that's the position and rotation, point scale, point color, point instance ID, and we'll get the count as well, get point count. So now we can pack up all of this into a compound Maya instancer, or 2 Maya instancer. And the node editor, I'll just get all of these arrays and hook them up. This can get slow at times, especially if you have lots of instances, but it's better than converting it to geometry. So now that we have that, we can grab our rocks, hide them maybe, but create a mesh network with an instancer. Here's the mesh network and the instancer node. So now we could go immediately from the point output into the mesh waiter, but I wanted to add a mesh Python node, which will also initialize auxiliary ports. Show attributes. This one, color up pp. So the script doesn't need to do much. It just needs this line to initialize the network and then commit the data, not changing it in any way. And now our instancer should show up. Oh, so I have to connect it. There they are. Cool. So let's create a plane and some lights. Now we can have a look if it is rendering. Here we go. And now for the color attributes. In the instancer, we have a Redshift rollout that allows us to input a particle shape as a reference. So make a particle. And I think we'll have to input the transform actually. And the particle shape doesn't have any particles yet, so I get the point count from Bifrost and make a nerve circle. Put this into sections, which will create a nerve circle with 2000 points, which is exactly the amount we have in Bifrost. And I'll put the curve into the particle shape as input geometry. And now our particles also have 2000 points. And then we can create an RGB PP value and an expression. And the expression will be mesh Python 1 dot color out pp. And just copy this over to runtime after dynamics as well. Create and create. And if you look at the particle shape, we should see some colors already. Let's hide it so we don't render the particles. And hit render. Now let's go into the shading network and add the add a Redshift shader. And I'll use a data color lookup. Let's get RGBPP and put this into the fuse color slot. And then I think we'll have to update the timeline once. Or maybe update the viewport. That's a pretty hacky way to get the color into Redshift. And I hope that we don't have to do this forever. That's just not working yet. Did I maybe need to add the particle shape? Yes, it's a particle shape, excuse me. So now we have our colors. So in the shading network, we can make use of this by rearranging the output. Let's take the art value, which is a random value from 0 to 1, and remap this. And maybe output not a range from 0 to 1, but 0 to 4. Take the Redshift shader switch and put this into the selector. And now we can put this into the color slot and dial in 5 different colors. So like red color, yellow color, green color, blue color, cyan color. There we go. All colors from 0 to 4 are mapped. And this is the way that I created the randomization. I randomized the colors with a palette like this, and then used the Redshift jitter node to randomize it even further. So we can put this color to diffuse, and we need to switch this to user data ID and take another remap node. And remap it to 2000, since we do have 2000 points. And output this to the user data. Yeah. And now each and every one will have a different hue, a different value, and a different saturation. Just have to set this up appropriately. Like this, maybe like this. And this way you can randomize everything. And then, you know, just keep going. Maybe make different materials. I'll make another Redshift materials. One will be the randomized color and opaque, and this one could also be random color, but with less reflection, a bit of roughness, and maybe we want some transmission, and also drive the transmission color. Then make another Redshift material and maybe use the gold preset, just like I did previously. get another shader switch, and input all of 3 shaders. Take another remap value node. Maybe take the green random colors now and remap it to 3. Take the value, put this into the selector. Oh, it's just up to 2. So now we're getting opaque stones, we're getting transparent ones with different colors. We're getting gold, or maybe that was a bad choice. Maybe let's take aluminum. And maybe just tone down the colors. They're a bit crazy. So more of a earthen palette will do. Yeah. And you can stack even more randomness on top if you want to map the displacement, for instance. Just make a couple of different maximum noises and mix those up as well. And then there could be another Redshift shader switch. And this time we make it a black material. Take another remap. Oh, we don't need a remap. We can just take the blue channel and put this into the selector. Which will take our black and white mask and apply it only where the white mask is 1, which corresponds to the shader slot 1, 0 being all the others. And yeah, here we go. We have randomized pretty much everything in the shading network, except for the displacement. I'll leave that to you to try out. And rendering instances in Redshift. Yay! So I hope you liked it, and it was a long one. Hope you could follow through, and have a nice day, guys. Bye.